And welcome back. So far we've shown how to use groups of spiking neurons to represent things, and the fact that connections can compute functions, and that recurrent connections can compute differential equations. Those are the basic components actually that we're going to build everything out of. So it's all going to come from those basic ideas. But just saying that really isn't enough. Just sort of saying, oh, okay, well now you can go ahead and implement algorithms as long as you can turn algorithms into vectors, functions, and differential equations. What I want to actually do now is sort of more give a hands-on example of building a really simple brain using those basic components. So this is going to be as simple a brain as possible, and I want to use it to sort of give examples of the sort of things that you go through when you're trying to put an algorithm into neurons, and how it's a little bit different from normal programming. So the goal we're going to have is to make a really simple brain that has really simple sensory system, really simple motor system, really simple little bit of memory, and a little bit of decision making. So I want to at least have those aspects, but in an incredibly simplified format. Okay, so here's the brain that we're going to try to build. It's a little critter that has one sensory input that sort of tells it what direction is food in and how far away is it, say. So that's sort of this is the direction that you should be going in, okay, if you want to go get the food or whatever it is. And if, and then it has another sensor that sort of says how scared you should be right now. So like maybe it's sort of like how bright is it right now. If it's if it's bright out, well, okay, there might be predators around. So if it's bright out, if it's dark out, okay, fine. Now you should go out and go find food, or vice versa, whatever. But then if all of a sudden, say it becomes very bright out, then it probably is a bad idea to go get food because, hey, creature, you're going to get eaten maybe. And so instead you should run back home. All right, so let me say that again. So normally you go in the direction the food is in, go find the food. And if there is some reason to be fearful, so if it's, if it's bright out, then run back to where you started from. Meaning, so in order to do that last one, that's where the memory is going to come in, because you're going to have to remember where you started from. Okay, that's the little brain that we're going to try to build. How the heck are we going to do that? All right, well, let's go back to Nengo. Let's give it a new file name. We'll call it critter. And we're just going to start with a completely empty model. And what exactly are we going to do? Model. So I like starting with the simple things that we know about. Started with simple sensory data first because, okay, at least we know what this is. Okay. So there's some sort of stimulus coming in that says what direction in the distance, or where's the food? And that's going to be two values. That's just going to be sort of an x distance, and a y distance. There's lots of other ways that we could do that, but it's just going to be two numbers. That's what's going to be coming in. Tell it, what's, is the food up, down, left, or right from where we are. Okay, and we're going to probably need a group of neurons to represent that information. That's going to be an ensemble. It's going to have some number of neurons. We'll do 100 neurons. and the dimensions is 2 because it has those groups of neurons have to store 2 things. And we're going to make a connection from the stim food to the food. Good. All right, let's do a quick check on that. If I make a little slider, and what we can probably do here is for the particular plot that we're going to pull up out of this one, we're going to do an XY plot because it's 2 values, and it's going to be just more convenient to sort of plot it that way. So this is saying, hey, there's food right where I am right now. If I move this slider up, okay, now we've got these neurons firing with some activity, and hey, there's food to my right. I should go that way. Or hey, there's food in this direction. Go that direction. Or there's food over here. Go in that direction. Okay. So this is totally normal so far. And as a reminder, so each of these neurons, if we, in this particular case, since it's a nice little 2-dimensional ensemble, if we went and actually looked at these individual neurons inside here, whoops, let's slow that down. There we are. What you'd actually end up finding is that that each of these neurons has some randomly chosen direction in this 2-dimensional space that it responds most strongly to, and that its activity changes. If the location is farther away from that point or from that direction, activity is going to change. This is exactly the classic Georgopoulos population encoding stuff. So that style of representation maps really well onto the brain, and that's part of why I'm using this sort of XY direction, or in order to indicate what direction the food is in, instead of having one slider mean, say, distance and the other slider meaning angle. I'm using this XY location because that seems to easily map onto the biology. All right, whatever. We have a group of neurons that's going to represent where the food is relative to me. So that's sort of a really simple input. And then let's have a really simple output. We're going to have a motor output. Neurons, 100, dimensions is 2, and that's going to be, we're just again going to imagine, all right, this is what command is being sent to my legs or to my motor system. Again, we're being as simple as possible. I don't want to go and simulate the physics of a leg and or arm motions or even a sort of wheel behavior, whatever. Now the nice thing is, if we wanted to, we can connect. Since Nengo is just a Python module, if we wanted to take any sort of simulator that exists that Python can talk to, we could just drop that in as well. For the purposes of this example, we're not. We're just going to say, hey, there's a group of neurons that's going to go and cause the agent to move with some velocity. Okay. And again, it's 2-dimensional, x and y. And now the simplest thing we could do is just make a connection from food to motor. Okay. And if we did that, this would be an incredibly simple version of the model where, hey, whichever direction the food is in, that's the direction the agent always goes in. All right. It's not quite what we want yet, but I like gradually building up the model and sort of running it in bits and pieces rather than trying to build the entire thing all at once. Okay. All right, so we have this. Now, we wanted some sort of, hey, if I'm scared, run back to where I started from. In order for me to do that, well, what do I need? Well, let's start with the sensory stuff. Okay, so we've got some input that says whether or not I'm scared. Oh, I can't type. There we are. Okay, and then we'll maybe have that mean something like, well, let's say we'll have it, because by default things are representing values between -1 and 1, what we'll do is say that if you're scared, if scared is -1, well, then you're not scared. So you should just go ahead and do whatever you were planning to do before. But if scared is +1, then that's when we want it to run back home. Okay. Again, we're going to want a group of neurons. Dimensions is 1. And we're going to want a connection from stim scared to scared. Cool. All right. So fine. We can scare the agent. Of course, scaring it doesn't do anything at the moment. Right. So how are we going to go and do this next step? If it's scared, it needs to run back home. How in the world are we going to know where home is? Okay. And actually, the way I think at least the way I phrased it back here, not home, I phrased it back here. Okay, move back to the starting location. All right. So the starting location. That doesn't help. How am I going to get back to the starting location? Well, hold on a second. We know what direction and speed we're moving in. That's this motor thing, right? Can I use that to try to keep track of where I am so that I know where to head back to? This is the sort of dead reckoning type behavior. This is the sort of experiments that people run on rats in lots of situations where they'll put them in an environment, let them run around, and then turn out all the lights and try to see whether or not it can navigate back home. So this is a sort of, can you internally keep track of where you are? And so we're just going to use that. In a more complex model, we would definitely also need to sort of use some sort of sensory inputs in order to try to figure out where we are. In the simple version, we're just going to use our own behavior as where we are. So we know what our velocity is. We know what command we're sending to our legs. How are we supposed to keep track of where we started? Well, let's say I have a group of neurons that's representing my position. We'll stick with 100. I'm sticking here. So when I tend to generally find that when I'm initially building my models, I will do something like, there's always this question of how many neurons to apply in each of these ensembles. The number of dimensions, that one's always sort of, well, I know what I'm trying to represent there. Am I trying to store one thing or two things or three things or four things, or however many things. For the number of neurons, that's a little bit more arbitrary. I tend to, just as a rule of thumb, do something like 50 to 100 neurons per dimension. Mostly because that gives me sort of a, how accurate is it representing those numbers? Something vaguely consistent on that. If I was using 100 neurons, or if I was using 50 neurons to do one dimension, if I then use those same 50 neurons to do two dimensions, it's going to do less good a job at representing those two dimensions. So there's going to be more noise in the representation, more of that jittery up and down. As if I scale things linearly like this, so if I double the number of dimensions, I'll also double the number of neurons. That at least keeps the accuracy in the right ballpark, or in a similar ballpark. If I was going to map this more onto biology, that I could do things like little experiments of like, okay, once I've got the model working, reduce the number of neurons and see how few neurons we can get away with, or something like that. I tend to use 50 to 100 neurons per dimension when I'm initially building it. So that's where I'm getting those numbers from. In any case, I have a group of neurons that's going to represent my position. How am I going to update my position? Well, really what I want this position to do is, well, if my motor is 0, then positions should stay the same. If I'm moving in one direction or the other, then position should move in those directions, should update in those directions. That should start sounding somewhat familiar to people. That is exactly an integrator, right? If this is velocity, position is the integral of velocity. this is exactly the same thing that I went and defined in as one of the examples in the section on recurrent connections. I also commented that an integrator is kind of nice because we don't actually need to remember all of the wacky math that I was showing before. We can actually build the integrator in sort of a somewhat intuitive way by just sort of saying, well, okay, look, if this is supposed to represent position, if my input is 0, then the position should continue storing whatever its position was. So I'm going to need a connection from position back to position, because something needs to take the data in position and send it back into itself. Right? If position is currently 0.5, and motor is 0, well, then the function from position back to itself should be the identity function. And that's what we're going to do. We're also going to use the rule of thumb that I mentioned in the previous lecture that, hey, when doing a recurrent connection, use a synapse with a longer time constant. It's what you find in the brain, and it makes the integrator more stable. Okay. So that's going to store my position. And then I want the motor system to update that position. Okay. And so that's just a connection from motor to position. Yeah, I may as well use the same synapse. All right. Let's shrink these things down a little bit, give us a little bit more space. Let's go there as well. That's all good, that's all good. Yay, yay. Put that up here. Make an XY plot. Okay, so first of all, let's run that and see whether or not we get anything useful. So we're staying still right now because, right, the food is indicated it's right exactly where we are right now, so the motor command is not doing anything. And so the position, it's drifting a little bit. You'll notice that, but it's mostly stable. And then I'm going to say, okay, go over to the right, and it goes to the right very, very quickly. And I say go to the left, it goes to the left very, very quickly. I would like to slow that down, right? Because it's right. So it is staying where I tell it to. I say go right, go left. It's going left. But if I move quickly, it very, very quickly hits the limit of what the position thing can represent. So I need to scale that down a little bit. So what I'm going to do is when I make this connection from motor to position, I could do something like this. Take whatever that value is and multiply it by 0.1. Okay? So if I multiply it by 0.1, that means whatever this does is going to change. We're going to change how quickly we're changing our position. All right. And you will notice also, so that should now take a second to go over there and come back. Okay. So if I go to the right, it goes to the right. If I go there, it goes to the left. If I go up, it goes up. If I go down, my position goes down. Okay. You will also notice, those people that were paying attention in the previous part of this lecture, I said that when you build an integrator, you're supposed to put a scaling factor of whatever your synapse time constant is on that feed-forward connection. And that's exactly what we've done here, right? And that's sort of another, so now that I put that feedback connection here, we can actually know that mathematically this is now actually an integrator in the sense that if I had an input of 1, then the value inside the integrator would go from 0 to 1 over the course of 1 second. That's just the definition of an integrator. If I change this number, then it will change the value in the integrator faster or slower. Okay, 0.1 is just going to be the value that from the math, if you wanted a mathematically exact integrator, That's what you should use. Otherwise, you get some scaled version of an integrator. Okay. So that's going to remember things. But now we're, before going on a little bit more detail, I also want to point out that, okay, this sort of function comes up a lot when building models. Is just sort of, hey, look, take whatever the value is and multiply it by some constant. Because that's such a common sort of function, we've gone and added a syntax to Nengo to automatically let you define things like that. So instead of saying function equals scale and defining this function, I can also just say transform equals 0.1. So for the special case of a linear function, so any function where you are taking your input and just multiplying it by a matrix, so in general it can be a matrix. In this particular case it's a 1-by-1 matrix, so it's just a single value. Then you can just quickly define things that way. Okay, so that's, but in terms of what actual network is created, it's the same network. But that's only saying, okay, so that means, okay, so we now have a system that represents our position. There's a couple things that we might want to improve about it before going any farther. So first of all, you'll notice that even when I put in a 0, 0, it drifts a little bit. Okay, the actual position that the creature thinks it's in, yeah, it looks like maybe it's stable right now, but if I say go up here a little bit and then say 0, yeah, it's going to drift a little bit. All right. Let's see if we can, so if we want to improve that, easiest way to improve that is let's just use more neurons in that integrator. Right. So 500 neurons. We might also want to increase the number of neurons in the motor population because that's what's giving the input to the integrator. So hey, sure, let's give a few more of those. Okay, and so we could go around and we can measure, well, how accurate do we get with certain numbers of neurons and things like that. But it comes up, go down. Okay, but we still have this problem that if we go too far away from our starting location, something weird happens. So first of all right, if we started, let's start back at 0, 0, let's get us sort of there-ish. Okay, if I go ahead and say, all right, go this way, it goes up that way, and then it hits some sort of threshold, and then it curves to the left for some reason. Well, what's happening there? Well, so first of all, why doesn't it go forever? And the reason it doesn't go forever is because neurons are good at representing things within some range. The default radius is 1, so it's not going to represent things outside of 1. All right, so that's at least why this representation doesn't keep going farther. Why does it suddenly curve back? So why is it that if I say come down here a little bit, whoops, there, and then I say okay, go this way, why does it do that? This sudden left turn thing? What's up with that? That's again part of this radius saturation behavior. Okay, the neurons are good at representing things not just between -1 and 1, but within a circle. They're good at representing points within this circle. That's the default in Nengo. You can adjust that. One of the parameters in the groups of neurons is what's the region to optimize over. And so you can adjust that to optimize over different regions if you feel like defining that. But since the default is a circle, if it starts trying to represent a value outside of that circle, it's going to represent a smaller value. And so that smaller value is going to be a little bit closer to 1. And so it's just the fact that when it hits this, when it starts going outside of that range, that normalizing, that thing that re-representation that's pulling it back closer to stay within the root unit circle is going to push things over to this direction. So this is all part of this weird radius. We are only optimizing over a certain range. Okay. Of course, if we want to increase that range, we just increase that range. Radius is 5. Now it should go right off the screen. So now we've got to right click on this and set the range that we're showing, -5 to 5. There we are. So now we've got a much larger space that it can represent. Yay. It's still going to hit that problem that if it tries to represent things outside of that space, it's not going to be very accurate. And it is still going to have this thing that when it starts representing things at the edge, it's going to get pushed to the side a little. Okay. There's all sorts of interesting, fun things that you can do if you want to try sort of making a space that wraps around on itself. It's just an interesting matter of figuring out, okay, how do you want to express that in math, and go ahead and implement it. Okay. Some of our some of the early papers in the NEF were looking at building path integrators of exactly this kind and dealing with problems like this. All right, so we can represent a position. There is a reason that we don't just set the radius to 10,000 and say, okay, you can represent all the space you want, because you will notice that as we increase that radius, the accuracy dropped. And so if we wanted to keep the accuracy the same, like when I started that off, let's actually show that. So back when we had 200 neurons and a radius of 1, right, when I started off, it looked like that. So let's go with 500 neurons. 500 neurons and a radius of 1. There we are. That's how accurate it's representing things. If I increase the radius to 5, all of a sudden our accuracy is much worse. That's because I'm using the same number of neurons to represent a much larger space. If I want to do a better job, I'm probably going to increase the number of neurons. And you will notice that as I increase the number of neurons, it takes longer to build the model, and longer to simulate the model, and longer to run the model. Start getting a situation where we want to start using GPUs and more complex hardware. We'll talk more about that in the next session. If you're running Nengo on your laptop, I would highly recommend not increasing the number of neurons in a particular ensemble to more than 3,000 or 4,000, maybe 5,000 if you're feeling lucky, mostly because of that build process. So when you press play, that's when it actually goes and generates the neurons and then goes and solves for all the connection weights. So when I press play, whoops, modify the model and then press play, that spinning gear, that's your computer generating all those neurons and finding all those connection weights. As you increase the number of neurons in one particular ensemble, that optimization process of finding the connection weights takes longer and longer. It's a least squares minimization problem. Having lots and lots of ensembles of about the same size, that's fine. But significantly increasing the number of neurons in one ensemble starts slowing things down. And you start needing, fancier hardware at that point. But we will stick with that. 500 neurons, radius of 5, range -5 to 5. There we are. Okay, so we can remember our location. What else are we going to do? Well, why did we do that? Well, our goal was to, hey, when we're scared, run back to where we started from. And when we're not scared, then we should go ahead and go to this particular position. Okay. Well, what's simpler to those? The simpler one out of those is, hey, let's only do this motor command. So this thing here that's going from where I think the food is to the motor, what I really want is I only want this connection to happen when I'm not scared. How can I do that? Because that's, so far I haven't introduced any interesting techniques for, having one group of neurons like disable other connections. And indeed, you'd have to sort of start postulating interesting, weird neuron mechanisms to have something like that happen. If all we have is standard neuron models, how in the world can we have a group of neurons, affect this connection? It seems like it's a thing that I haven't covered. Interestingly, it is something, though, that I have covered. It is exactly something you can do using the techniques that I've already shown. And the idea, one way to think about it is, really what we now want is that the function that is taking us from food to motor is not just a function of food. It's a function of food and whether I'm scared. And so if I want to do some sort of function I want what's going on in the motor to be a function of both of these two things, both food and scared, then really what I want is, instead of making a direct connection from food to motor, I want to make it an intermediate group of neurons here that represents both food and scared, and then coming out of that intermediate group of neurons, we go to the motor thing and compute whatever function we wanted. Okay. That's sort of like the trick that I used in the first lecture about how do you implement multiplication. Okay, so what do we mean by that? So let's say let's make a group of neurons called "Should we do the food?" It's going to be three-dimensional. Or maybe we'll call it go food. Or I don't know what we're going to call it. It's an action. It's whether or not we should, or it's going towards the food if we're scared. All right, so that's why I'm going to call it do scared. It's got to store, in order to implement that function, I need to know both scared and both of the food things. All right, so the dimensions is going to be 3. Okay, I need to make connections. I need to send all the information from food, so that's both dimensions from food are going to go to do food, and one of the dimensions from scared is going to go in there. In order to do that, I'm going to use the same sort of, so I mentioned in the earliest lecture that in order to pass information into particular dimensions, we could define functions for each of those, but there's also syntax, special syntax for that in Nengo for defining those functions. So we're just going to use those. I'm going to make a connection from scared to do food 0. Okay, so that's saying of the 3 dimensions in do food, the first one is being affected by what's in scared. And then we have a connection from, so what I could do is I could say, well, the first dimension in food goes to do food 1, and the second dimension goes to do food 2, right? That's what we want. I want to pass both of those things across. You can also write that as, well, okay, that's both things from food. So that's both dimensions from food, and I want that to go into dimensions 1 and 2 in do food. Okay, that's one way to write it if you're used to that sort of, this is the standard square bracket syntax for NumPy for doing that in Python. Another way that some people might be familiar with writing it is like that. Whoops, sorry. too many square brackets. So that's saying don't put that into the 0th dimension. Dimensions start counting at 0 because Python is a programming language that's counting at 0. So it's it'll go into dimension, into the next ones. So Python notation for slicing, implement that any of the ways that is more intuitive to you. So that gets all the information into doFood. But now what function do we want to compute on that? And we'll call this doFood function. So this doFood function, this has 3 variables, and we could refer to those 3 variables as x0, x1, and x2. I find I'm going to get confused if I do that, so I tend to, whenever I'm doing a complicated function in Nengo, I tend to give all of my variables useful names. So I know that the first variable is scared, or the first dimension is scared, the second dimension is food x, and the third one is food y. Okay, so that's Python syntax for take x and split it. And now I have 3 variables that are the 3 different things in x. So now I can have more readable functions. And now what do I want this function to do? Well, I want it to do just exactly what we were saying. Well, if I'm scared, if scared is greater than 0, then don't go to the food. Otherwise, if I'm not scared, then go to the food. Okay, it's a little bit weird. It's a function. It's just this is the exercise of taking algorithms, the things that we would normally be describing as it's just sort of commands and algorithms, and trying to turn it into a mathematical function such that the neuron's can approximate that function and do what we want. Okay, so this sort of thing is what we end up with. And we have a connection now from doFood to motor, and the function is the doFood. Okay. Now this is also a situation where looking at the diagram like, oh, whoop, okay, now that we've built that one, I really need to get rid of the connection directly from food to motor. That's one of the nice things of having the diagram up here, is helps me at least vaguely remember to do that. So now I'm going to delete that. All right, does that work? All right, well, let's find out. So first of all, we're going to need a slider for the sim scared. Here we are, and we're going to run that. Okay, so I'm not scared. Food is in some direction. Everything seems to work fine here. All right, you can say go up, it goes up, go down. Maybe a little bit of a weirdness here, where we're seeing, hey, I'm moving food straight up and down, but there seems to be some weird curve that's introduced into the motor. There's actually a reason for that, and we will fix that in a moment. Think on it for a moment. But we do seem to have this basic behavior. We're still moving around and chasing after the food. I go ahead and scare the system. And now all of a sudden, when I start changing my food, my agent has frozen. It is not moving anywhere. We're still not at least running back home, but we've got this first phase of, hey, motor has stopped changing. All right, and then if I make it not scared again, well, now it'll go ahead and chase after the food again. Okay, so there it is. It's running, it's moving, it's moving, it's moving, it's chasing after the food, chasing after the food, chasing after the food. Then I scare it, and it freezes. Okay. But there's some weird effects going on in this. And let me see if I can generate that weird effect again. So I'm going to scare, no, I'm going to, he's not scared. And I'm going to go over there. Let's go. All right. So I'm moving the food in a straight line up and down. And we're getting this really quite pronounced curve in the motor system. All right. So what is causing that? Most of the time when some weird behavior is happening, the answer is, oh, it's something to do with the radius. I'm going to go into a little bit more detail on this one because I think it's an interesting example of the sort of debugging that you'll end up doing when building a model. Because sometimes when I'm building a model and I see this weird effect like that, I'm like, okay, is it that the neurons are messing up somehow, or did I mess up defining my function? Okay. And one quick thing Nengo lets you do to check that is any group of neurons, I can tell Nengo, hey, that, let's change the type of neurons here to not neurons at all. And there's a command, so they're just called direct. So what does that mean? That means this ensemble of neurons, forget that they're neurons. They're not neurons anymore. Just compute this bloody function exactly as I've defined it. All right. So this would be a quick way of finding out, was it that I messed up defining this function? Or is it something to do, or is it just the fact that the neurons are only trying to approximate the function and the neurons are messing up and doing a bad job of approximating the function? So if I just do that we're now in direct mode, and I go ahead and move this up and down, all right, we're getting way less pronounced. We're still getting some, but we're getting way less pronounced big giant curve. All right, that's fine. So it's probably to do with the neurons. So whenever I see something like that, it's probably now to do with the neurons in that group of neurons. And what I maybe need to do is increase the number of neurons, and maybe that will help. In this particular case, though, it's something else, and that is, hold on a second, what's the radius of this group of neurons? So this group of neurons is supposed to represent, has a radius of 1, but my input, this, like the three things that are stored in here, one of them is this direction to food, one of them is this scared thing. We're definitely going to have values outside of a radius of 1 here. Right. So I'm going to increase that radius. I mean, technically, if you wanted the food, if you wanted everything to be able to be values between -1 and 1, then that would give you a radius of square root 3. So you'd probably want a radius, of around square root of 3. Because the food is already representing things in a radius of 1. This is going to have a radius of 1. Scared is going to have a radius of 1. So that means this do food is really just going to have a radius of square root of 2. So I'm going to say a radius of 1.4 is good enough. And then we're going to get rid of this direct mode. Because direct mode does not involve neurons, the radius is irrelevant there. But in any case, now if we go with our neurons, scared, let's go put it into that same example. And now we should have a much straighter up and down. Okay, so we're now doing a much better job of approximating that function because we've actually told it to, optimize over the right range of values. All right, so we have a thing that can go ahead and run around, and we can scare it, and when we scare it, it freezes. That's not quite the behavior that we want. What we want is that when we scare it, it runs back to where it started from. So in order to do that, to run back to where we started from, it's something kind of like this food circuit, but the opposite, right? And instead of using the direction that food is coming from, we want to use the direction that position is coming from. So we're going to do the same trick. All right, we're going to grab, we'll just grab these again. We're going to say do home. I'm scared to do home. And we don't care about the food information, we care about the position information. That's what's going to go in. Oh, whoops, and that should be good to do home. There we are. There we are. This is our position. Put you, I don't know, up here. We've got this do home thing. All right, so that's got all the information from position and scared going into it. We're again going to do something very similar to this, but it'll be a different function. We'll call this the do home function now. And it's not got food X and food Y, it's got position X and position Y. And do home, do motor, do home function. All right. And now we've got to go ahead and change this function. So if I am scared, what should I be doing? If I am scared, I should go, I know what direction what point I'm at, so if I want to go back to where I started from, I want to go to minus position X minus position Y. And if I'm not scared, then this thing should do nothing. Okay. So if I am scared, this one will be doing something, and this one will be outputting 0. If I'm not scared, then this one will be doing something, and this one will be outputting 0. All right, is that going to work? Save it, find out. All right, so I'm currently not scared. I'm saying going that way. Now let's make this bigger so that we can actually see it. Let me put this. It's always fun trying to organize these diagrams. Here we are. All right. So I'm saying, hey, go that way. It goes that way. Hey, go that way. Go to the right. It goes to the right. Go up. It goes up. Go down. It goes down. It's going down, it's going down, it's going down, and then I'm going to scare it, and it runs back to where it started from. All right, the position is now 0. And then we don't scare it, and now it can go, it's free to go ahead and wander off again. And go in different directions, wandering over that way. Then we can go ahead and scare it. And it's going to run back home. And it runs back home. And you'll even notice there that as it was getting closer to home, it slowed down a little bit. Right, the motor slowly came back towards 0, which wasn't technically anything we programmed in here, but that's entirely due to just the fact that the neurons are just approximating these functions. Cool. All right. So I hope that was a useful little example of how to implement a tiny little brain. You know, it's something like 1,000 neurons. It's got this weird structure. I find that when we build models very quickly, you get these sorts of structures where things are connected all over the place, and you get these weird, fun, recurrent loops and things. It just tends to happen when you're building interesting behaviors. But now we have something very much like, you know, some simple sensory system, simple motor system, a simple little memory, and this sort of really simple decision process. There's going to be lots of that, so that idea is there. There's going to be tons of things to learn and improve about that process. And that's sort of going to be covered in the later lectures in this series. For example, things like, this process that I'm showing here of having, you know, these two actions, that's not going to scale very well if I'm going to go up. If I want like 10 different actions it could do. Those are going to get really complicated to define. How am I going to interact and get those things to interact a little bit better? So that's going to be one important thing that'll be coming up. But the core idea of how we can build up things and turn algorithms into functions all looks like this. All right. So that's the main trick of taking these sorts of ideas that we initially described in words, this sort of in this sort of way, and converting it into functions and differential equations. And we can do that. And my claim is that that's the only trick we're going to need in order to build up some pretty large-scale brain models. And so that's the question. Is that enough, what I just described there? Now, what about cognition? And these are the things that we're going to need to cover in other lectures. It's all going to turn out to be just what we described here, but we're going to want to spend a little more time on it. So for instance, given what you've seen here, how in the world can you do something like language? How can you do something like the cognition and symbolic reasoning and symbol structures? How are we going to take algorithms that are very symbolic like that, which are the foundation of a lot of psychology and cognitive science theories? How are we going to translate those into the components that I just saw? How are we going to use vectors to represent symbols and manipulate symbols by making computations on those vectors? Another big one is going to be that cognitive control, such that thing of, okay, in this situation, route the information from one brain area to another. So what we just saw, for instance, what we just implemented with the critter, in some situations, when it wasn't scared, we wanted to route the information from the sensing food part of the brain to the motor system. But then in other situations, we wanted to route the information from the memory of where home is part of the brain to the motor system. How do we make that scale up? How do we do that for complex tasks? How do we do that in situations where there's lots of different things going on? That will be a separate one of these lectures, and it will turn out to map pretty nicely onto the cortex basal ganglia thalamus loop. And another really big one that we're going to want to talk about is, what about learning? And what do we mean by learning in particular there? In one sense, everything that I just showed there, yes, there was learning involved, because there was an optimization process in order to find the best connection weights to run the task. But once we started running the model, there was no learning while the model was running. So that's usually, or at least a distinction that's often done, is that are we talking about online learning or offline learning? The offline learning that is currently happening in all of these models, that happens when you press play, the gear spins, and then the model's created and off it goes. Similarly, in a lot of deep learning sorts of models, you go do your optimization process, you go do your backprop, your gradient descent, you get your connection weights, and then you go ahead and use the model later. That's not really how biology works. Biology often maybe sort of starts with some connection weights, but then adjusts those connection weights while you're behaving. And to a certain sense, it's going to be easy to add that to these models, because once we generate the models, it's just a normal neural network, and so you can go ahead and put in any sort of neural network learning algorithm. But what we're going to be doing when we look at it is sort of saying, well, hold on, if those learning algorithms are modifying the connection weights, then they're implicitly modifying the functions being computed. And that's going to give us a slightly different way of thinking about putting in what sorts of learning rules to add. Okay. So that's going to be the plan. And just to sort of whet your appetite, yes, we are going to be able to build up some pretty complicated things using just the components that you saw here. So for instance, this is spawn adding 4 plus 3, and it's adding by counting. It's doing 4 plus 3, and then it's mentally thinking 5, 6, 7, and then writing the number 7. Every single step in that is all just things that you have seen already, or normal neural network stuff, and that includes the vision, it includes the motor control. The memory is actually a 512-dimensional version of the integrator that we just showed. That's sufficient for that task. We can do that. We can also do a little bit of a reinforcement learning task. So this is a task where whenever a question mark appears, the agent is just draws a number, And then we either show it a 0, in which case it gets no points, or we show it a 1, in which case it gets 1 point. And eventually what it does is it learns that, hey, whenever it draws a 2, we often give it a point. Right, so this is a sort of a very standard, oh, hey, this is a standard sort of reinforcement learning task that's done on animals relatively often. And it even works even if there's the occasional, oh, sometimes when you draw a 2, you don't get a point. It's still like, nah, I'm still going to draw 2s. Right? That was done by doing this sort of use an online learning rule that goes and adjusts connection weights between neurons. The most complex task that we will end up doing and talking about in this course is the Raven's progressive matrices. This is also I would argue, the most complex cognitive task that we've implemented in this sort of large-scale brain model. What is this task? This task is, I'm going to show you a pattern, okay, and we're just showing it a number at a time. I'm showing that pattern in the bottom left, so just so that you and I can sort of look at that pattern and go, okay, well, what comes next? And I think you can already tell, all right, what's it going to do? 5, 5, okay, what's going to come next? And the agent is quite willing to write out 5, 5, 5. How do you write an algorithm for that? All in terms of vectors and functions on vectors. That's what we will need to cover. And that's where we will go in the next few lectures. So thank you very much, and we will see you next time.